The foundation: understanding internet speed measurement. Before we dive into the glorious evolution of internet speeds from painfully slow to absurdly fast, we need to establish something fundamental that trips up nearly everyone. When your internet service provider advertises 100 megabits per second, most people assume they can download a 100 megabyte file in 1 second. Spoiler alert, they cannot. Not even close. The confusion exists because internet speeds are measured in bits per second, while file sizes are measured in bytes. And here is the kicker: it takes 8 bits to equal 1 byte. Always. This is not negotiable. So when you see 100 megabits per second advertised, you need to divide that by 8 to get your actual download speed in megabytes per second. That gives you 12.5 megabytes per second. Suddenly that massive number does not look quite as impressive, does it? Let's break this down with real numbers. If you have a 1 gigabit per second connection and you want to download a 1 gigabyte file, it will take you 8 seconds, not 1 second. 8. A 15 gigabyte file. That is 2 minutes. If you have 500 megabits per second, downloading a 500 megabyte file takes 8 seconds, not the 1 second your brain desperately wants it to be. This is not false advertising, technically. The networking industry has always measured speeds in bits per second since the internet began. But let's be honest, advertising bigger numbers sells better, and most consumers have no idea they need to divide by 8. So yes, it is misleading even if it is technically correct. The best kind of correct if you are an internet service provider. Now that you understand the single most important concept about internet speeds, let's walk through how we went from connections that could barely load a text email to speeds that sound like science fiction. The dial-up era, when the internet moved at the speed of molasses. Let's start where it all began: dial-up internet. The era when connecting to the internet meant nobody in your house could use the phone, and downloading a single song could take 20 minutes. Good times. The earliest dial-up connections used something called baud rates, which measured how many signal changes happened per second. Connections started at 300 baud in the 1970s, then crawled up to 1200 baud in the early 1980s. These used acoustic couplers, which were basically devices where you physically placed your phone handset into rubber cups. Yes, you had to manually stick your telephone into a modem. The future was weird. These connections were excruciatingly slow because they were transmitting digital data over analog phone lines that were designed for voice, not data. The phone network was never built for this purpose, which is why it performed exactly as poorly as you would expect. By the 1990s, dial-up reached its evolutionary peak, the 56 kilobits per second modem. You might remember brands like US Robotics or Hayes if you were old enough to have emotional scars from this era. That 56K number sounds impressive until you realize it translated to actual download speeds of about 5 to 7 kilobytes per second in real-world conditions. Why could dial-up never go faster than 56K? Physics. The analog phone lines had fundamental limitations in how much data they could carry. Phone line noise, signal degradation, and the limitations of analog to digital conversion meant 56K was essentially the ceiling. You could not squeeze more speed out of those copper wires without completely changing how the system worked. At 56 kilobits per second, downloading a 4 gigabyte file would take approximately 1 week, assuming of course that AOL did not randomly kick you off your connection, which it absolutely would, and assuming nobody in your house picked up the phone, which would instantly disconnect you and force you to start the entire download over from scratch. Dial-up was less of an internet connection and more of a test of human patience and emotional resilience. But dial-up did something important. It proved people actually wanted internet access at home, even if that access was painfully slow. This created demand for something better. Early broadband, the first real speed upgrade. Eventually, technology evolved beyond torturing phone lines into transmitting internet data. Enter broadband, which was a fancy term for internet that does not make your phone unusable. The first broadband options were digital subscriber line, better known as DSL, and cable internet. DSL arrived in the late 1990s and offered speeds ranging from 0.5 megabits per second up to about 8 megabits per second. This was a massive jump from 56 kilobits per second dial-up. Suddenly, you could download a song in under a minute instead of waiting half an hour. Revolutionary. DSL worked by using the same copper phone lines as dial-up, but it used different frequencies. Voice calls used low frequencies, and DSL data used higher frequencies, which meant you could talk on the phone and browse the internet simultaneously. This was genuinely mind-blowing in 1999. Most DSL connections were asymmetric, meaning download speeds were much faster than upload speeds. This technology was called asymmetric digital subscriber line, or ADSL. You might get 6 megabits per second download, but only 512 kilobits per second upload. The reasoning was simple. Most people download far more than they upload. Watching videos, loading websites, downloading files, all downloads. Uploading was mostly just sending emails, which are tiny, but DSL had a fatal flaw: distance. The farther you lived from the telephone company's central office, the slower your connection became. If you were more than 3 miles away, your speed dropped significantly. And if you lived in a rural area, good luck getting DSL at all. This distance limitation is ultimately why DSL faded into irrelevance. Cable internet, on the other hand, used the coaxial cables that brought television into your home. Cable companies realized they could transmit internet data over the same lines, carrying 200 channels of content you never watched. Cable internet launched in the late 1990s and offered speeds from 10 megabits per second up to 100 megabits per second or more. Cable used a technology standard called Data over Cable Service Interface Specification, or DOCSIS, which sounds like a pharmaceutical drug, but is actually just the rulebook for how cable internet works. DOCSIS evolved through multiple versions, with each iteration supporting faster speeds. DOCSIS 3.0 could hit 1 gigabit per second under ideal conditions. DOCSIS 3.1 pushed that even higher. But cable internet had its own problem: shared bandwidth. Your neighborhood shared the same connection, which meant during peak hours when everyone was home streaming videos, your speed could drop significantly. If you paid for 150 megabits per second, you might only get 75 megabits per second at 8 p.m. when everyone was watching Netflix. Cable companies oversold their capacity because statistically, not everyone uses their full bandwidth at the same time, except when they do. Despite these limitations, cable internet became the default broadband option for millions of people. It was fast enough, widely available, and significantly better than dial-up. For about 2 decades, cable dominated the residential internet market. The fiber revolution, light-speed internet. Then fiber optic internet arrived and made everything else look like a joke. Fiber optic cables transmit data using light instead of electrical signals. Actual pulses of light traveling through glass strands thinner than a human hair. This is not an exaggeration. This is how fiber works. Because light travels significantly faster than electrical signals and does not degrade as quickly over distance, fiber optic connections can deliver speeds that cable and DSL cannot even approach. Early fiber deployments offered 100 megabits per second, which was already impressive, but fiber scales in ways copper cables simply cannot. Fiber connections are also symmetrical, meaning your upload speed matches your download speed. If you have 500 megabits per second download, you also get 500 megabits per second upload. This was a game changer for anyone who needed to upload large files, run a business, live stream content, or back up data to the cloud. Suddenly, upload speed was not an afterthought. Fiber also has dramatically lower latency than cable or DSL. Latency is the delay between when you send a request and when you get a response. For online gaming, video calls, or anything requiring real-time interaction, lower latency matters more than raw speed. Fiber connections typically have latency around 10 to 20 milliseconds, while cable might be 20 to 40 milliseconds, and DSL could be 30 to 50 milliseconds or higher. The gigabit era began when internet service providers started offering 1 gigabit per second fiber connections to residential customers. 1000 megabits per second. Remember, divide by 8 to get real download speed. 125 megabytes per second. At that speed, downloading a 10 gigabyte file takes about 80 seconds. A 50 gigabyte video game downloads in under 7 minutes. Gigabit fiber became the gold standard for home internet. It provides enough bandwidth for an entire household to stream 4K video on multiple devices, download massive files, run video calls, and game online simultaneously without anyone experiencing slowdowns. This is the speed tier where internet stops being a bottleneck for most normal activities. But fiber did not stop at 1 gigabit. Many providers now offer 2.5 gigabit, 5 gigabit, even 10 gigabit residential plans. At 10 gigabits per second, you are downloading at 1,250 megabytes per second. That 50 gigabyte game, 40 seconds. A 100 gigabyte file transfer, 80 seconds. Of course, at these speeds, your equipment becomes the bottleneck. Most consumer routers, network cards, and devices cannot actually handle 10 gigabit speeds. You need specialized hardware, but the infrastructure is there, waiting for devices to catch up. Fiber is the current pinnacle of residential internet technology. It is faster, more reliable, lower latency, and symmetrical. The only downside is availability. Running fiber optic cables to every home is expensive. So many areas still do not have access. But where fiber exists, it is unquestionably the best option. Mobile internet evolution, from barely functional to actually fast. While home internet was evolving from dial-up to fiber, mobile internet was having its own awkward adolescence. The early mobile networks were not designed for data at all. They were built for phone calls. Asking them to transmit internet data was like asking a bicycle to compete in a car race. 3G networks were the first mobile connections that could handle internet data in any meaningful way. 3G launched in the early 2000s and offered speeds ranging from 1 megabit per second up to about 10 megabits per second under ideal conditions. In reality, reality, you were lucky to see 3 to 5 megabits per second. At those speeds, you could load basic web pages, check email, and even watch low-quality video if you were patient. YouTube launched in 2005, right as 3G was becoming widespread, and early mobile YouTube was a pixelated, buffering nightmare. But it worked, barely, and that was enough to prove people wanted internet access on their phones. Then 4G and LTE arrived, and everything changed. LTE stands for long-term evolution, which is a hilarious name because it implies this technology will be around for a long time. It was not. But while it lasted, LTE was genuinely impressive. 4G LTE launched around 2010 and offered speeds from 20 megabits per second up to 150 megabits per second or more in ideal conditions. Suddenly, mobile internet was actually fast. You could stream HD video without buffering, download apps in seconds instead of minutes. Video calls actually worked. Social media became dominated by video content because mobile networks could finally handle it. LTE made mobile internet competitive with home internet for many basic tasks. If you had a strong LTE signal, you could legitimately use your phone as a mobile hotspot and run a laptop off it. This was the era when people started questioning whether they even needed home internet, especially if they lived alone and used their phone for everything. But 4G had limitations. In crowded areas like stadiums, concerts, or dense urban environments, speeds dropped dramatically because too many devices were competing for the same towers. And latency, while improved, was still around 30 to 50 milliseconds, which was acceptable, but not great for real-time applications. Enter 5G, which is less of an upgrade and more of a complete redesign of how mobile networks function. 5G comes in two flavors, sub-6 GHz and millimeter wave. Sub-6 operates on lower frequencies, offers moderate speed improvements over 4G, and covers wide areas. Millimeter wave, or wave, operates on extremely high frequencies, delivers insane speeds, but only works over very short distances. Real-world 5G speeds vary wildly, depending on which version you are connected to. Sub-6 5G might give you 100 to 400 megabits per second, which is a nice improvement over LTE, but not revolutionary. Millimeter wave 5G, when you can actually connect to it, can hit 1 to 2 gigabits per second. That is faster than most home internet connections. The problem with millimeter wave is that it cannot penetrate walls, trees, or even heavy rain very effectively. You need to be close to a tower with clear line of sight. This makes it perfect for stadiums and dense urban areas, but useless for most suburban or rural locations. 5G also dramatically reduces latency down to 10 to 20 milliseconds, or even lower. This low latency is what enables things like cloud gaming on mobile devices, real-time remote control applications, and smoother video calls. When latency is low enough, the delay becomes imperceptible. The reality of 5G in 2025 is that your actual experience depends heavily on where you live, which carrier you use, and which version of 5G your phone connects to. It is not the revolutionary upgrade the marketing promised, but it is a meaningful improvement over 4G Wi-Fi evolution. Wireless internet inside your home. Having fast internet coming into your home is pointless if your Wi-Fi router cannot distribute it properly. Wi-Fi technology has evolved through multiple generations, each one desperately trying to keep up with the increasing speeds of home internet connections. The earliest Wi-Fi standards, now retroactively called Wi-Fi 1 and Wi-Fi 2, were basically proof-of-concept technologies. They were slow, unreliable, and had terrible range. Wi-Fi 3 improved things slightly, but none of these early versions could handle more than 54 megabits per second under perfect conditions. In practice, you were lucky to see 20 megabits per second. Wi-Fi 4, also known as 802.11n, launched in 2009 and was the first version that felt truly usable. It could theoretically hit 600 megabits per second using multiple antennas, though real-world speeds were more like 100 to 200 megabits per second. This was enough to stream high-definition video reliably, which was the main thing people cared about. Wi-Fi 5 or 802.11 AC arrived in 2013 and pushed theoretical speeds up to several gigabits per second. In reality, most people saw speeds between 200 and 600 megabits per second depending on their router quality and how far they were from it. Wi-Fi 5 operated primarily on the 5 GHz frequency band, which offered faster speeds but worse range than the older 2.4 GHz band. This created a fundamental Wi-Fi problem. The 2.4 GHz band had better range, but was slower and more congested because every microwave, baby monitor, and Bluetooth device also used it. The 5 GHz band was faster but did not penetrate walls as well. You had to choose between speed and range. Wi-Fi 6, technically 802.11ax, launched in 2019 and changed the game. It did not just increase raw speed, though it did that too. Wi-Fi 6 improved efficiency, allowing routers to handle more devices simultaneously without everyone speed tanking. This mattered because the average home in 2025 has dozens of Wi-Fi devices: phones, tablets, laptops, smart TVs, streaming boxes, security cameras, smart speakers, thermostats, light bulbs, and appliances. Wi-Fi 6 made all of them work better together. Wi-Fi 6E took things further by adding access to the 6 GHz frequency band, which was brand new spectrum with almost no congestion. If you had a Wi-Fi 6E router and Wi-Fi 6E devices, you could get gigabit wireless speeds reliably throughout your home. The catch, of course, was that both your router and your devices needed to support 6E, and in 2025, many devices still do not. Wi-Fi 7, the latest standard, pushes theoretical speeds even higher, well into multi-gigabit territory. It is designed for homes with 10 gigabit fiber connections, where even Wi-Fi 6E might become a bottleneck. Wi-Fi 7 can theoretically hit speeds over 40 gigabits per second using all available spectrum and advanced technologies like 4096 QAM modulation, which is a fancy way of saying it crams more data into each transmission. But here's the reality. Most people will never need Wi-Fi 7. If your home internet is 500 megabits per second or less, Wi-Fi 5 or Wi-Fi 6 is perfectly adequate. Upgrading to Wi-Fi 7 only makes sense if you have multi-gigabit fiber and devices that can actually use those speeds. Otherwise, you are just spending money on overhead you will never utilize. Beyond consumer speeds, the backbone of the internet. Everything we have discussed so far is consumer-facing technology, the speeds you and I can actually purchase for our homes or phones. But underneath all of that is a completely different world of network infrastructure operating at speeds that make gigabit fiber look quaint. When you stream a video from Netflix, download a file from Google Drive, or load a website, that data is not traveling directly from the company to your home. It is moving through a vast network of data centers, undersea cables, and backbone connections that operate at speeds measured in terabits per second. A terabit per second equals 1,000 gigabits per second. At this speed, you could theoretically transfer 125 gigabytes every single second. That is enough to download every video uploaded to YouTube in an entire day in under an hour. These are not consumer connections. This is the infrastructure that powers the entire internet. Major tech companies like Google, Meta, Amazon, and Netflix move data between their data centers at multi-terabit speeds. This is how Netflix can simultaneously stream millions of 4K videos without the whole system collapsing. This is how Google can serve billions of search queries per day. The backbone infrastructure is orders of magnitude faster than anything reaching individual homes. Data centers themselves use 40 gigabit, 100 gigabit, and even 400 gigabit network connections between servers. Inside a single data center, information moves at speeds that would let you transfer your entire computer's hard drive in under a second. These connections use specialized fiber optic cables and networking equipment that costs more than a luxury car. Undersea internet cables connecting continents also operate at terabit speeds. These cables, laid across the ocean floor, carry the vast majority of international internet traffic. When you access a website hosted in another country, your data is likely traveling through one of these undersea cables at speeds exceeding 100 terabits per second on the newest installations. Then we enter the realm of experimental speeds that exist only in research labs. Scientists have demonstrated petabit per second connections, which equal 1,000 terabits per second. At 1 petabit per second, you could transfer 125 terabytes every second. That is enough bandwidth to stream every video on YouTube simultaneously. This technology is not commercially available yet, but it proves that current speed limits are nowhere near the theoretical maximum. Researchers in Japan demonstrated a record-breaking 1.02 petabits per second transfer in 2025 using advanced fiber optic technology that is 10 million times faster than the average home internet connection. At these speeds, distance becomes almost irrelevant. The bottleneck is not the cable. It is maintaining data integrity and preventing errors when moving information that fast. Beyond petabits, we have exabits, which equal 1,000 petabits per second. No current infrastructure operates at this speed. This is purely theoretical territory. 1 exabit per second equals 125,000 terabytes per second. You could transmit every video ever uploaded to YouTube in a few seconds. This is the kind of speed that might one day connect planetary-scale AI systems or enable real-time Earth simulations. Even further beyond are zettabytes and yottabytes per second, speeds so absurdly high that they exist only as mathematical concepts. At 1 yottabyte per second, you could download the entire internet in under 1 second. There is no physical infrastructure that can handle this. These are speeds that might only exist in quantum data transfer systems or neural-level communication technologies in the distant future. The point of discussing these extreme speeds is not that you will ever have a yottabyte connection at home. You will not. The point is that internet speed is constantly evolving, and what seems impossibly fast today becomes normal tomorrow. 20 years ago, a 1 megabit per second connection was considered broadband. Today we consider gigabit speeds standard and are already deploying multi-gigabit residential fiber. The trajectory is clear. Speeds will keep increasing. If you want to understand what's actually happening beneath all these speeds, check out the 7 levels of internet.